Hello, everyone. Today I'm going to talk about controlled channel attacks, deterministic side channels for untrusted operating systems. This work was partly done when I was an intern last summer at Microsoft Research with Weidong Cui and Mark Spinado. In a typical computer system, applications run on top of operating system, and the OS has been considered the software root of trust. However, there are often reasons why we don't want to trust the OS. First, legacy commodity operating systems have very large code bases, and people have found endless security bugs in them. These bugs will leave vulnerabilities in the system, which might enable some external attacker to install some rootkit into your system that steals the user's data. In a different scenario, suppose the user or a company wants to create a website. Today, it's increasingly popular that he will just use just run a web server on a cloud service. In this case, the cloud provider has full control over the operating system running in it. But if the cloud provider is either malicious or compromised, he can abuse this control to steal the user's data. In order to solve these problems, researchers have proposed several systems to remove the operating system from the trusted computing base. We use the term shielding system to refer to these type of systems. And they typically use a hypervisor or some secure hardware to confine the OS such that the applications are shielded from the potentially malicious operating system. For example, Overshadow and InkTag are hypervisor-based shielding systems, while Haven is a relatively new system based on Intel SGX. SGX is a new security feature proposed by Intel for its future CPUs. One of the key protections they provide is to protect the application memory pages from the OS and guarantee both secrecy and integrity for these pages. That means the OS can't steal or tamper with the data inside these pages. Another important feature for this shielding system is that they support to run legacy applications on a legacy operating system with very small or even no modifications. The OS is not eliminated from the software stack. Instead, it's still needed for some core functionalities, such as resource management. This is because the OS is supposed to run many applications efficiently, and the resource management is a non-trivial task in this case. In particular, with shielding systems, the OS is still responsible for memory management, even for protected applications. It's responsible for managing the page tables of all the protected applications. But the shielding system will likely add some integrity checks on every page table update. Now, with shielding systems, all your applications are protected from a potentially malicious operating system, and they still enjoy the rich functionalities provided by the operating system. However, in this talk, I'm going to show you that existing shielding systems are insufficient to provide the security guarantees they claim. Here are some highlights of our results. First, suppose the user has a secret treasure map in a JPEG format. In order to display it, he has to decode it using some standard library, like JPEG. And we found that even if he runs the JPEG decoding in a protected application, the malicious OS can still learn a sketch of the image from where you can clearly see the destination of the treasure. And second, suppose the user got a secret message, and he wants to display it using some font rendering library like FreeType. We found that the OS can actually reconstruct the whole message with perfect accuracy. And last, suppose the user wants to spell check a text file using tools like Hunspell. We found that the OS can actually reconstruct most of the words in the document, although some words have the affixes removed. In our experiment, we spell checked the entire novel, The Wizard of Oz. We found the attacker can get around 96% of accuracy. So you must wonder how we could achieve this. The short answer is side channel attacks. In our scenario, the attacker is the operating system. Because the OS controls the victim applications running in it, we use the term controlled channel attacks to to refer to our new type of side channel attacks. We show it's more powerful than traditional side channel attacks, where the attacker is some unprivileged process. In a traditional side channel setting, the victim has some secrets protected, and the attacker doesn't have direct access to them. But the attacker might leverage some side effects made by the victim, such as the timing of the cache access, power consumption, or network traffic, in order to infer some knowledge about the secret. However, a common drawback of these traditional attacks is that they're subject to severe system noises like context switches, TLB flushes, exceptions, and page faults. As a result, the attacker usually gets a very noisy result. In contrast, in our case, the attacker is the operating system. It controls all these system events. For this reason, it can leverage noise-free side channels from the victim. In particular, because the OS is still responsible for managing the page tables for protected applications, we use page faults as a side channel. The power of this side channel is that it is completely deterministic. The OS controls the page tables, and it can set a trap at any page by making it inaccessible. And it doesn't even need to do timing to tell whether a trap has been triggered. On the other hand, we do have a new challenge here, which is the page faults only tell page granularity information as opposed to cache line granularity. However, we found that even with this coarse-grained side channel, the attacker is able to reconstruct very fine-grained application data. The basic idea is to use input-dependent memory accesses. For example, if the application code contains such a branch where the input is a branch condition, additionally, if different branches are located in different memory pages, then we will observe different page fault sequences when different branches are taken. So based on the page fault sequence, we can tell whether the input is true or false. Another example is the application reads one element from a big array, where the index is the input. If the array spans across different memory pages, then based on page faults, we can tell a range about this input. Next, I'll use Hunspell as an example to show how we can use this basic idea to extract application data. Hunspell is an open source spell checker. It's used in many popular applications like LibreOffice and Firefox. The way it works is very simple. At initialization, it loads a dictionary file into a big hash table. Here, we assume the dictionary is known. The hash table is implemented in a standard way called separate chaining. You can find the definition of separate chaining in many textbooks of data structures. And as you see here, there are two parts in the hash table. The first part on the top is an array of pointers, where the index of each element corresponds to a unique hash code. Then each element points to a linked list, which contains all the words sharing the same hash code. And this is a very standard way to deal with hash collisions. So all applications using similar data structures will have the same type of vulnerability. The first step of our attack is to track the page faults of the loading phase of the dictionary. Based on these page faults, we can learn some page-level knowledge about the memory layout of the hash table. But we'll skip the details here and focus on the next step when Hunspell checks the spelling of the input file. For every input word, Hunspell will perform a hash table lookup. And here on the left, this is a simplified code snippet for the spell checking routine. For each input word, it computes the hash in order to locate a linked list. Then it traverses the linked list trying to find a matching word. If a match is found, it reports success. Otherwise, it reports failure. So suppose we have a simple input which has 3 words, side channel attack. Then for the first word, it computes a hash code, and using that hash code as an index to read an element from the pointer array, this will trigger a page fault at page 4. then it traverses the linked list, which contains only a single word. And this will cause a page fault at page 7. Similarly, for the next word, channel, we'll get page faults at 1, 5, and 6. For last word, attack, we'll get page faults at 3 and 5. Now we have a page fault trace. The next step is to divide it into segments such that each segment corresponds to a single word in the input. Well, there are many ways to do this, but the simple approach we use is to leverage the hash function. The hash function is located in a different memory page, and it's invoked for every input word. So we can use the page fault at that page as a separator in our page fault trace. Now, for each segment, we can learn the original input word based on our knowledge about the page level structure of the hash table. The key of this attack is the hash function. The hash function is supposed to shuffle the words in an order that appears random, and it has very low correlation with the words in the linked list. As a result, we get very low ambiguity in our attack results. Here's a quick summary of our attack results. We have implemented 3 attacks against Hunspell, FreeType, and libjpeg on both Haven and Intag. For Hunspell, when we spell check the entire novel, The Wizard of Oz, we got around 96% of accuracy. For FreeType, which is a font rendering library, we got perfect accuracy for any English input, including letters and punctuation marks. For libjpeg, here's a list of image pairs. In each pair, the left image is the original one, and the right image is the one we recovered from the page faults. Clearly, the reconstructed images still tell a lot of information. Our attacks add a lot of page faults to the execution of applications. And page fault handling is expensive, especially in systems like Intag. So our attacks have non-trivial overhead. However, they are still realistic to execute. For example, with our attack enabled, Hunspell takes less than 3 seconds to check the entire novel. And for FreeType, it only takes less than around half a second to render a 5 kilobyte text file. We believe that these small runtimes are sometimes unnoticeable by the user, especially in the cloud scenario where the background noises are significant. Finally, I'd like to share some thoughts on partition mitigations. Unfortunately, at this point, we don't have great ideas we don't have great off-the-shelf solutions. If we do the defense on the application side, we might want to rewrite the application in order to hide page-level access patterns. We could do this either manually or with the help of a compiler. For example, the developers of OpenSSL over the years have changed the implementation of some small security-critical functions in order to prevent cache-based side-channel attacks. However, the shielding systems are trying to protect complex, large legacy applications. So the cost to rewriting them completely will be very high, including engineering effort and performance overhead. On the system side, we might want the shielding system to add more restrictions on the behavior of the operating system. For example, we can restrict the way the OS performs memory management. However, this may affect some functionality provided by the OS or the transparency provided by the shielding system. With these difficulties, I'd encourage the community to rethink the challenges for Overshadow's initial vision, which is to protect legacy applications from legacy untrusted operating systems. In conclusion, an untrusted operating system can construct noise-free side channels for the applications running inside of it. The page fault side channel leaks large amounts of information about legacy applications. For this reason, control channel attacks must be addressed in the design of future shielding systems. Thank you.
We have plenty of time for questions. I had one quick one. So you demonstrated on InkTag and Haven, and is there going to be any problems porting the attacks to SGX?
Yeah, we implement the attacks on both InkTag and Haven. Haven is based on SGX.
Oh, okay, good. That's a good point. Great. So that was a dumb question. Anyone have some better ones from the audience? Help me out up here. All right, well then let's thank this. Oh, we do, yes. It has to be better than the last one though.
I'll try hard. Matthias Peyer, Purdue. I wonder how useful your attack is if you don't know the actual code that is being executed. This will restrict in the form and the places where you can put page faults and the information that you get from that attack.
Yeah, that's a good question. I didn't mention this in the talk, but we do rely on the knowledge about the binary. And actually, for our to ease our hacking, we actually use the source code of the applications. But I don't know if this is a fundamental limitation.
Well, you could imagine a small TCP component that loads the executable image from some trusted machine.
But in that model, do you mean when application executes, it is still isolated from the OS? But that's not the target of our attack. Our attack is, the target of our attack is when the application runs on top of the OS, not isolated from the OS.
Okay, thanks.
It's a much better question. Any others? All right, why don't we thank the speaker again.